Okay, so let's unpack this. AI just made its own language. Should we be afraid? That's,
Yeah.
well, it's a question that really grabs you, doesn't it?
It does, and it's natural to feel, a bit uneasy when AI starts doing things we think of as uniquely human.
But what's really interesting here, and maybe less scary when you dig in, is that this isn't some sudden rogue AI thing. It's tied to how AI has evolved.
Exactly. Over the past decade or so, we've moved from AI that just labels images to these much more dynamic systems, multi-agent
Where
systems.
multiple AIs interact.
Right. They learn together, sometimes cooperating, sometimes competing. And in those settings, especially using reinforcement learning, you know, trial and error or unsupervised learning,
When they just find patterns on their own.
precisely. In those cases, we've seen these communication protocols, these sort of mini languages, just emerge spontaneously.
Okay, languages in quotes there.
Yep.
Key to understand, these aren't like English or French. They're not for us.
Not at all. They're purely optimized for the AI agents to get a specific job done more efficiently, whatever that job is.
Which is why we wanted to do this deep dive, right? To get past the headlines.
Mm-hmm. We want to look at the reality. What are these communication methods, really? How do they actually arise? What are the genuine risks versus the hype? And what safeguards are people working on?
And we're basing this on the actual technical findings, the research papers in this field.
Yeah, digging into the research. So let's set the scene a bit more. This shift you mentioned from static classifiers to multi-agent systems.
Yeah, think less lone genius AI, more AI team working on a project.
That's a good way to put it. And in these teams, especially when they're learning through rewards, this communication thing just starts happening.
It's not programmed in explicitly like Agent 1 say X to Agent 2.
Nope. It arises from the learning. They discover that sending some kind of signal helps them achieve their goal better.
And again, the signals they come up with, often totally opaque to us, not human readable.
Right. So how does it happen? Let's talk multi-agent reinforcement learning, MARL.
Okay.
You've got multiple agents learning together, maybe cooperating on a task, maybe competing. And often, crucially, they have some kind of communication channel available to them.
Like a way to send messages back and forth.
Exactly. And during the learning, they figure out that using this channel, sending something, helps them coordinate and, well, get better results, get higher rewards.
Like a basketball team developing hand signals.
Sort of, yeah, but mathematically driven. The key mechanism involves something called differentiable communication layers.
Okay, differentiable, meaning calculus is involved.
Basically, yeah. It means the way they communicate is part of the network that we can adjust smoothly during training using backpropagation. The same process that teaches the AI what actions to take also teaches it what messages to send.
So it's learning how to talk and what to do simultaneously.
Pretty much. This leads to this idea of backpropagation through communication.
Right, you mentioned that. Unpack that a bit.
Right. Okay, so Agent A sends a message. Agent B receives it and uses it along with its own observations to decide its action.
Makes sense.
Now, if Agent B's action leads to a good outcome, a reward, the learning signal flows back, not just to tweak Agent B's decision-making, but also back through the message all the way to Agent A's messaging part.
Whoa. So Agent A learns to send better messages based on Agent B's success.
Exactly. It's this feedback loop specifically for the communication itself.
That's wild.
And over thousands, millions of trials, the messages evolve. They become these super efficient encodings of whatever information is most critical for that specific task, that specific environment.
Okay, so what do these efficient encodings actually look like? Are they like zeros and ones words?
Well, that depends. Early work often used discrete protocols. Think like choosing one symbol from a fixed set, maybe represented as a one-hot vector, like 00100.
A limited vocabulary.
Right. And sometimes researchers could analyze these, cluster them, and get a rough idea, like maybe symbol 3 often appears when the target is red or something,
Yeah.
a bit more interpretable for us.
Okay, interpretable but maybe limited.
Exactly. So newer stuff often uses continuous embeddings. Instead of discrete symbols, the message is a vector, a list of continuous numbers like 0.23, -1.5, 0.8.
Which can hold more information, higher bandwidth.
Much higher bandwidth, yeah, more nuance, but
Much harder for us to understand what those numbers mean.
precisely, that's the trade-off. More expressive communication for the AIs often means less interpretability for the humans looking over their shoulder.
Got it. Okay, so this isn't just theory. You mentioned experiments.
Oh yeah, several landmark ones. Lewis et al. back in 2017 did these referential games.
Referential games.
Yeah, like Agent A sees an image, has to send a message to Agent B, so Agent B can pick that same image out of a lineup.
And they developed their own signals.
They did. They developed these token-like messages that seem to correspond to visual features. Not quite words, but functional symbols for the task.
Huh.
Okay, what else? OpenAI's hide-and-seek experiment in 2019 was fascinating. The agents learned complex tool use and coordination strategies, all emergent. Communication wasn't explicitly enabled, but their behavior implied that if it had been, you'd likely see some pretty sophisticated protocols arise.
The potential was clearly there.
Definitely. And then Couture et al. In 2017 looked at multi-round negotiation dialogues.
Like AI haggling.
Kind of. Agents had to negotiate resource allocation over several message turns, and they developed, actual negotiation strategies, ways to open, counter-offer, concede all without being told how dialogue works.
Wow, so not just single messages, but back and forth strategies.
Exactly. These really show it happening in practice.
Okay, let's get slightly more technical then. What are the building blocks of one of these emergent protocols inside the AI?
Sure. Typically, you've got a few key parts. First, an embedding layer. Takes the raw input pixels, game state, whatever, and turns it into a more abstract internal representation, a vector.
Like the AI summary of the situation.
Kinda, yeah. Then a message encoder, usually a small neural net. It takes that internal summary and cooks it down into the actual message to be sent. Often a fixed length vector, maybe using something like Gumbel-Softmax to help with exploration during learning.
Gumbel-Softmax? Sounds complex.
It's a trick to allow gradient-based learning with discrete choices, basically. Helps explore different message options.
Okay, so encode the message, then it goes through the channel.
Right, the message channel could be that discrete vocabulary we talked about, or a continuous vector space. That's the medium.
And then the receiver.
The receiver has a message decoder, another network. It takes the incoming message, combines it with its own local observations, and uses all that to figure out what action to take. It outputs probabilities for different action logits.
Observe, embed, and send via channel det receive, decode, decon, NAC, act.
That's a great summary loop. And tying it all together is the loss function.
The goal the AI is trying to optimize.
Exactly. It usually balances two things. First, maximizing the task reward, doing the job well. That's often represented as minimizing negative reward.
Makes sense.
And second, there's often an entropy term for the messaging. This encourages the AI to, use its messaging options to explore different ways of communicating rather than just settling on one potentially suboptimal message forever.
So perform well, but also keep exploring communication. Lambda balances those.
Yep, Lambda is the hyperparameter controlling that balance. It shows how deeply linked the communication is to the task optimization.
Which really brings us back to why calling it language can be misleading.
Hugely misleading, yeah. Because human language has semantics, grammar, its general purpose. These AI protocols, not so much.
They lack semantics by design, you're saying.
Right. They are purely optimized for a specific task, a specific Markov decision process, if you want the technical term. The meaning of a message is entirely context-dependent and task-dependent.
So symbol X could mean go left in one game, and it's a cat in another.
Absolutely. There's no shared underlying meaning system like we have. It's all about what works right now for this problem.
And trying to map their symbols back to our concepts is hard.
Often incredibly hard, yeah. The mappings can be totally opaque unless you specifically design the system for interpretability or do a lot of post hoc analysis. It's often just weird numerical signals that happen to work for the AI.
Efficient for them, cryptic for us.
Yeah.
Which leads naturally into the risks and maybe some misconceptions. This idea of security through obscurity.
Yeah, the worry is, okay, if AIs develop secret codes, couldn't bad guys use that to make them do bad things without us knowing? Covert commands hidden in the emergent language.
Sounds plausible.
Well, the catch is to really understand and manipulate these messages effectively, you generally need access to the AI model's internals, the weights, the architecture.
Which you hopefully wouldn't have if you're a bad actor.
Hopefully.
Yeah.
But the concern shifts slightly with black box APIs. Could adversarial AIs probe a system, interact with it enough to kind of reverse engineer parts of its communication protocol without seeing inside? Maybe. It's an attack surface to consider.
Okay, so not straightforward, but a potential vulnerability.
Yeah.
What about unintended coordination?
Right. This is the fear that maybe Multiple AIs, even if not designed to be malicious together, might just stumble upon ways to cooperate via emergent communication that amplify harm.
Like two separate scam bots figuring out how to coordinate a more complex fraud.
Exactly that kind of scenario. Phishing attacks, market manipulation. If rogue AIs can spontaneously team up using their own code, that's a multiplier effect for the threat.
Scary. How do we stop that?
Mitigation involves things like sandboxing, keeping AIs in controlled environments, careful audit logging of communications, maybe restricting the communication channels themselves, limiting their bandwidth or complexity.
And then there's the big existential stuff, the sci-fi fears. Secret AI language means Skynet is coming.
Understandable why people go there, but, the reality check is important. Current emergent protocols are narrow, task-specific, often brittle. They break if the context changes slightly.
That the flexible general communication of a superintelligence.
Not even close at this stage. So that specific fear seems overblown based on current tech, but that doesn't mean we dismiss the whole area.
Right. We need safeguards and ways to actually understand these things better. Interpretability.
Yes, and there's active research here. One approach is trying to ground the communication.
Grounding.
Yeah, like forcing the AI to use symbols we understand. Maybe constrain their vocabulary to English words or even emojis. Or add extra training objectives that reward messages matching human labels.
Guiding them towards human understandable communication.
Exactly. Another angle is working on the AI architecture itself, trying to encourage disentangled representation. Trying to make the AI learn internal concepts that are independent, so maybe one part of the message vector consistently relates to object color, another to object shape, making it easier for us to decode, using things like variational bottlenecks.
Okay, trying to structure the meaning. What about decoding languages that already exist?
That's where techniques like interactive probing come in. You train another AI, a probe network, to look at the messages being passed between the first set of AIs. You give the probe network examples of messages and the context, maybe some human labels, and it tries to learn what the messages correlate with.
Like an AI linguist trying to decipher the first AI's language.
That's a perfect analogy. And then, more broadly, there's the regulatory side, standardizing red teaming exercises.
Red teaming. Like ethical hacking.
Sort of, yeah. Having independent teams specifically try to find ways AIs could misuse emergent communication for unauthorized coordination, proactively searching for vulnerabilities.
Makes sense. Okay, so let's circle back to the big question, all this considered. Should we be afraid?
Short answer. Not imminently afraid of, world domination via secret AI code, but vigilance is absolutely critical.
It's a capability, a tool.
Exactly, a powerful one. Think of the good uses. Coordinating fleets of autonomous cars for smoother traffic, managing swarms of drones for disaster response, optimizing sensor networks. Huge potential benefits.
But also potential for misuse if we're not careful.
Right. The same mechanisms could be turned to harmful ends without oversight, which puts a big responsibility on the AI community.
What should the community be doing?
Well, transparency is key. Publishing details about communication channel designs when possible. Developing industry standards for auditing these protocols, benchmarks for testing.
And education.
Definitely. Educating policymakers, engineers, the public about what these AI languages actually are and aren't. Getting beyond the hype to the technical reality.
So the main takeaway seems to be, these emergent protocols are a natural result of optimizing AI for complex tasks in multi-agent settings. They're not magic, not sentient plotting.
Correct. They're a fascinating product of the learning process. Powerful, yes. Potentially risky if ignored, yes. But not inherently malicious or a sign of runaway superintelligence right now.
It's about balancing the potential benefits with careful oversight and continuing to develop those safeguards and interpretability tools.
That sums it up perfectly. Which leaves a final thought, maybe, for you listening. As AI agents get better and better at developing their own ways to communicate, even if just for specific tasks, what does that mean for our future interactions with AI? How do we ensure we can trust, understand, and safely manage systems that might be talking in ways we don't immediately grasp?
Definitely something to keep thinking about as this technology continues to evolve.